All right, so this is Math 150, Section 2, Lecture 8. We're going to do optimization today. So my goal, which is typical for this class, is to concentrate on concepts from Calc 1, Calc 2 that you've hopefully seen before, and do the proofs in great detail there, and then just talk briefly about how it extends up to Calc 3. I found over time that most people do not have a very solid background on why things work in calculus. And so I want to concentrate on those items. So the first question is optimization. So we're searching for maxima and minima. For places where the function is largest and smallest, how do you find in calculus where a function is largest or smallest? So check critical points. We'll see how well this works. Okay, tell me when you think I'm moving fastest. Right. So the hope is you will never, ever, ever make that mistake again. The answer is incomplete. What do we need to complete the answer? Yes? Check endpoint. I'm really glad I only have to do this lecture twice. Check endpoints. So promise me you will never ever forget again to check endpoints. All right? Sometimes it is clear that the endpoints cannot be the maximum or the minimum. I'll be curious later to see if that actually dented the wall. All right. Now, in one dimension, is it a big deal to ask you to check endpoints? Why is it not a big deal in one dimension? At most two, right? Maybe you have the whole real line, or maybe you're going from 0 to infinity. So you have, at most, 2 endpoints. And then the critical points, these are x such that f prime of x equals 0. So the question is, why does this work? And so I want to talk a little bit about why critical points give you candidates. And that's the key phrase here, is these are candidates. These are not certainties. These are not saying these points will be maximum, these points will be minima. They're just saying if there are maxima and minima, these are the only options. So let's look at the derivative. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. Let's assume f prime of x is greater than 0. So we're assuming we have some point where the first derivative is positive. All right? Well, if the first derivative is positive, if h is sufficiently small and positive, we know f prime of x is positive, the denominator is positive. What must be true about the numerator? It must be positive. Then f of x plus h is greater than f of x. So if we are in a situation where the first derivative is positive, for h sufficiently small, we know that if we go a little bit further, f of x plus h will be larger than f of x. Could x be the place where f is maximized? Well, here's x, here's f of x. Because the first derivative is positive, we know if h is sufficiently small, f of x plus h has to be a little bit larger. Could this be a maximum? No. Also, if we go in the other direction, if h is negative, then the numerator has to be negative, and you get f of x plus h has to be less than f of x. So it has to look something like this. So if the first derivative is positive, you can't be a maximum or minimum. Similarly, if the first derivative is negative, you can't be a maximum or minimum. So the only way you can have a maximum or minimum is if the first derivative is 0. So now we have to talk about the difference between a necessary condition and a sufficient condition. A necessary condition to pass my class is to take my class. There are some classes where people have passed without actually taking it. It's interesting. Do you think enrolling in the class is sufficient to guarantee that you pass? No. So there's a difference between a necessary condition and a sufficient condition. The necessary condition is that the first derivative is 0. If the first derivative is not 0, you clearly cannot be at a maximum or minimum unless you're at an endpoint. So I can have a very positive first derivative there, and that could be the place where my speed is maximized. Okay. So this gives us an idea of why the first derivative is so useful. Let's consider f of x is x cubed. So I get f prime of x is 3x squared. So what are the critical points? When does 3x squared equal 0? When x equals 0. Critical point is x equals 0. Do we have a maximum or minimum? No, neither. So if you plot x cubed, it's going to look like this. The first derivative is positive coming up to 0, and then it's positive beyond 0. So what I often like to do is here's maybe, if you want to think of it as x, here's f prime, here's the critical point at 0. How many of you have seen graphs like this? We can draw f prime and f double prime below. How many of you have not seen this before? How many of you are not aware? But your hands are moving at the right time if you're asleep, so that's good. So when I was young, they used to teach us plotting like this. This is the 21st century. If you get a function to plot, what should you do? Should you make dots on a piece of paper? No, what should you do? Use a calculator, use a computer. This is the 21st century. I want you to have some idea of how to get a quick sense of what a function is. And the ability to do quick curve sketching is very valuable. And we will maybe later in the semester see a really great optimization problem that uses almost every technique from Calc 1. Great optimization problem, has applications to how computers are built, and comes down to being able to graph things. And these are graphing functions that have variable parameters, so it's tough to put this in a computer. If I look down here at f prime, whenever the first derivative is positive, my function's increasing. So I know this can't be a maximum here. So this leads to the first derivative test. And so we'll do now the first derivative test, we'll do the second derivative test, quickly review these. Now for a lot of things, when you have candidates, if you don't have that many candidates, just check them all and see which one is largest, see which one is smallest. The more candidates you have, the more painful this is. In one dimension, it's not a big deal. There's only 2 endpoints at most. Once you get into higher dimensions, unfortunately, then you could have an entire curve as the boundary. Or you could have a surface, and it becomes much, much harder, and we'll learn techniques to deal with that. So, first derivative test. We'll assume f and f prime exist and are continuous. So here's f prime. Here's some point x naught. Let's assume x naught is a critical point, and let's assume the first derivative is 0 here. Let's assume my derivative is positive in a small neighborhood to the right and negative in a small neighborhood to the left. Well, if I want to plot things, what must be true of my function as I move a little bit to the right? It has to be increasing. I don't know how, but it's going to look something like that. What if I move to the left? What should I see? I'm sorry? So if I move to the left, it should be getting lower?
The slope. Yeah, the slope is negative.
The slope is negative. So what is that? So as I move to the left, am I going up or am I going down?
Slope is positive. Slope is positive.
I'm going up. See, my function is decreasing. So I have to start high and then low. Right? So because my first derivative is negative, I have to start up some higher point and come down like that. So by just knowing what the first derivative looks like near the critical point, just by knowing the sign, I can give you a quick sketch of what my function looks like. And I can see that this must be a minimum. So if it goes negative 0 positive, it's a minimum. Any questions on the first derivative test? All right. So the first derivative test is great to use if you can easily determine what the sign of the first derivative is. If you can't determine the sign of the first derivative, it's not a great test to use. The advantage of the second derivative test is you only need one number. But now you also need the second derivative to exist. So we'll say f prime and f double prime are continuous. And so here's my function. Here's the first derivative. Here's the second derivative. I'll assume I have a critical point at x naught. And now, let's assume the second derivative is positive. If you want, think of it, it takes on the value 18. So we're going to assume the second derivative is positive at the critical point. What must be true about the second derivative if I move just a little bit away from x naught? What can you tell me about the value of the second derivative? So what should it be if I'm very, very close to x naught? It should be approximately what? So the second derivative, let's assume it's 18 at x naught. And the second derivative is continuous. So if I move a very small distance, approximately what value should the second derivative be? Approximately 18. If I move a large distance, what should it be? No idea. But if I move a small distance, it's got to be very close to 18. If I move a little bit to the left or the right, it's got to be close to 18. If it was positive here, if I move a really small distance, it has to stay positive. So because we're assuming the second derivative is continuous, if I move an extremely small distance, it can't change. Imagine you're driving on the highway. Your first derivative is your speed. Your second derivative is your acceleration. So you slam on the brakes and your car starts to decelerate. So your second derivative is now negative. Can your second derivative go from being negative to being positive instantaneously? No. You'd have to take your foot off the brake, put it on the accelerator, and start giving the car gas. But you're decelerating, so it's going to take a little bit of time to stop that. So you're not going to be able to instantaneously change. If I'm positive here, I'm going to be positive in a small neighborhood. Okay, the first derivative tells you about whether or not your function is increasing or decreasing. If my first derivative is positive, what happens to my function as x increases? So it's increasing. So I know the second derivative is positive here. What function does the second derivative tell us about? The first derivative. So if the second derivative is positive, what do you know about the first derivative? Okay, so I want to know more in terms of what's happening to the values of f prime.
So you know f prime is increasing or decreasing.
Right, so if the second derivative is positive here, is f prime increasing or decreasing as I go past x naught? It's increasing. Because the second derivative tells me if the first derivative is increasing or decreasing. Since it's positive, the first derivative is increasing. All right, let's look to the left of 0. The second derivative is positive, so as I approach x naught, is my function increasing or decreasing? Increasing. So what values must I have over here? Yes? It must be negative, because I'm increasing. If I was positive, I can't increase to 0. If I'm at 5, I can't increase up to 0. I have to be negative, maybe negative 2, and increase all the way up to 0. And now we've done our favorite technique. We've reduced this to a previous problem. What does this now look like?
Minimum.
It looks like a minimum, but where have we seen this picture before? Yeah. So I'm doing this lecture much better than section 1. I actually drew them on the same picture. But here, section 2, we can fix all the flaws from the first iteration. This is now the first derivative test. So we have a minimum. So it's going to look something like this. And so explicitly, you get if f prime of x naught equals 0, then if f double prime of x naught is greater than 0, you have a min. If f double prime of x naught is less than 0, you have a max. So to use the second derivative test, you have to be able to take the second derivative. You need the function to be continuous. And you have to remember, if the second derivative is positive, does that mean min or max? Yes? So if the second derivative is 0, we don't have enough information. And then you have to go to the third or the fourth derivative test. And so if you go back to the function we had, x cubed, the second derivative would be 6x, which would be 0 at 0. So the second derivative would vanish, and this would give us no information. So unfortunately, the second derivative does not always give you information. But if it exists, it's a really easy check. The hardest part is remembering which is the minimum and which is the maximum. How often, and I feel like somebody on like the Home Shopping Network, do you find yourself in a situation where you remember most of a result, but not all of it, and are trying to remember the last little bit of details? I mostly remember this formula, I mostly remember this chemical compound, I mostly remember this historical date. I'm going to show you a way that if you mostly remember, you can actually refine it and fully remember. So all you need to remember is that there is a second derivative test. What we're going to do is we're going to look at a very special function. And if we can figure out what the second derivative test should be for that special function, then we'll know what it must be in general. So let's consider actually two functions. So we'll consider g of x is x squared, and h of x is negative x squared. I have chosen these functions carefully because I can plot them. That's the upward parabola. This is the downward parabola. G prime of x is just 2x. G double prime of x is just 2. H prime of x is negative 2x. H double prime of x is negative 2. Is this a maximum or minimum? Minimum. And this is the maximum. So if you can't remember which way does the second derivative test go, does it indicate a maximum or minimum, test it on something you know. I know the parabola. I can calculate the parabola pretty quickly. And so when I do the parabola, I say, g double prime is 2, it's a minimum. Okay, if the second derivative is 0, then it must, if the second derivative is positive, it must be a minimum. If the second derivative is negative, it must be a maximum. So there are a lot of things, fortunately, like this in mathematics, where if you mostly remember something, if you check a special case, you can often use that to fix things and make sure you have the right formula. Okay, so this is the basis of how we do our tests. So now let's apply this to a couple of problems. So there was a request to do the Farmer-Brown problem, so we'll talk about that in detail. I'll do Farmer-Bob problem very briefly, and then we'll move on to the Farmer-Barbara problem. How many of you have read the book Click, Clack, Moo, Cows That Type? All right, I got this request too late to bring in the book, but I sometimes start off the class by reading from that book. Anybody remember the first line of Click, Clack, Moo for cultural extra credit? Farmer Brown has a problem. Can you give me the next line? I think it's all day long his cows like to type click, clack, moo, click, clack, moo, click, clack, moo. It's been a while. My kids are now much older. I can still do, I think, at least the first 1/6 of Cat in the Hat. All right, Farmer Brown. So Farmer Brown has a problem. He actually has two problems. The main problem he has is he wants to maintain a pen to enclose his cows. The other problem is he seems to have a fixation on rectangular shapes and will consider nothing but a rectangle. So we'll leave that for other people. He will only consider rectangular pens. And so given a perimeter of 40, you want to maximize the area. And this is the same as you're given x plus y equals 20. Because if I tell you the whole perimeter is 40, then that's the same as half the perimeter is 20. So as stated, this is a constrained maximization problem. And for those of you who are interested in economics, we will eventually do Lagrange multipliers, which talks about how to solve problems like this very well using multivariable calculus. Right now we haven't done multivariable constrained problems. So we need to somehow convert this to a one-dimensional problem. Any thoughts on how we could convert this? Yes?
You can write y in terms of x.
Could you write x in terms of y?
Yes.
Would you want to? No. I mean, most of us have a tendency, right? Is it wrong to write x in terms of y and solve in terms of y? No. But most of us would not do that. Most of us would solve for y in terms of x and substitute. And I think we would still do this even if the algebra was a little bit nicer for solving for x in terms of y. We just have a tendency to make x the variable. Doesn't really matter. Yes?
Put everything on one side and take the partial.
Well, we haven't done partial derivatives yet for problems like this. Right now we're trying to reduce this to a one-dimensional problem. And so what makes this a hard problem in several variables is we're not just trying to maximize x, y, but we're trying to maximize it subject to this condition. And the fact that there's a constraint makes things much harder. But you are right that later on we will be taking partials. So we can find y is equal to 20 minus x. So this gives us the area function x times 20 minus x. And what's my range for x for this problem? Yes?
Like in terms of x, like x has to be greater than or equal to 0 and less than or equal to 20.
Good. So since x plus y is 20, x can't be more than 20. Do I have to check the endpoints? Yes, in principle I have to. But looking at this, if I choose a rectangle with no length or no width, there's no area. I know that's not going to be the maxima. So a lot of times we're lucky and we know the maxima is going to be the interior point. All right, what do we do now? I'm sorry? So what do we do now? How do we finish this?
Expand it.
Expand it. Why expand?
To take the derivative.
To take the derivative. So if we were to take the derivative of this now to find the critical points, we have to use the product rule. If we expand, we get 20x minus x squared. So I will make Thoreau a verb. You Thoreau it. How many of you are familiar with Thoreau's Walden Pond? What was the great advice he gave people? You're much more knowledgeable than the first section on Thoreau. What was the great advice Thoreau gave people?
You say expand, expand, expand.
Almost.
Is it the other way around?
Simplify, simplify. Now you could simplify, simplify, simplify to simplify, but it's worth being a little bit redundant to emphasize the point. Simplify, simplify. This is really good advice. Whenever you're given a problem, take a few moments and look at it and see, if I spend a little bit of time, can I make the algebra better so that I do less work later on? And here, by doing a little bit of simplification, instead of doing the product rule, I now get to do the difference rule, or the subtraction rule, whichever way you want to call it. It's much better. So to find the critical points, I look at a prime of x, which is 20 minus 2x equals 0. That implies x equals 10, which then implies y equals 10. And as a shock to everyone, it's a square. Okay? So we were able to reduce the Farmer-Brown problem to a one-dimensional calculus problem. We are not always going to be so fortunate. All right. I'm not going to spend too much time on the Farmer-Bob problem. So for Farmer-Bob, Bob is very similar to his brother Brown, except Brown lives in the Great Plains and Bob lives by a giant lake. And because of that, he doesn't have to put in an extra side. He gets one side for free. So this is done in the video, so I'm not going to spend too much time. When Bob is trying to figure out what rectangle will maximize the area, given that he only now needs 3 sides, the best way to do this is to imagine which superhero? Aquaman. And so while Bob is building his pen for cows, Aquaman is building his pen for fish. Whatever rectangle is optimal for Bob is optimal for Aquaman. And so if you look at this, it's now just a giant rectangle with twice the perimeter of before. So this would have to be a square. And so if we have 40 meters, it would now have to be 20 by 10. So I really love being able to use the symmetry principle like this. All right, so this was Brown, this was Bob. We're about to move on to Barbara. Before we move on to Barbara, I want to talk a little bit about multivariable optimization. Now, this is a vast topic. And again, the biggest problem with multivariable optimization is dealing with the boundary. In one dimension, the boundary is trivial. But once you get to several dimensions, it becomes a real pain. So imagine you have some shape like this. You need to figure out what are the interior candidates and what are the boundary point candidates. Okay? So the interior candidates are actually fairly straightforward. The boundary candidates are very painful, but we will find a way to do that later. So imagine this point over here was a local maximum. What does it mean to be a local maximum? It means if you go any direction from it, a small amount, you will never get a higher value. If it was a local minimum, if you go a small distance from it in any direction, you will never get a lower value. So let's say we have a local maximum. What must be true at a local maximum for our differentiable function? So it's the highest value, but I want a condition. So in one dimension, how did we find interior maxima? What did we look for? The first derivative equals 0. What should we look for here?
Second derivative be negative.
Well, no. Well, we're still trying to find candidates, so we're not at the second derivative yet.
Maybe partial derivatives?
The partial derivatives. So no matter which direction I move, if it's a maximum, it can't get larger, right? Why not just move parallel to the x-axis? So if I just move parallel to the x-axis, let me get some of my steps in, right? I just move parallel to the x-axis. I now have a function of one variable. How do you find an interior critical point for a function of one variable? Its first derivative must be 0. What does that mean because I have a function of two variables? Well, I'm holding y constant. So I must have df dx equals 0. If not, it can't be a maxima. And now if I just move in the y direction, what would I find? So now I guess I have to move this way. So now if I move this way, what must be true? What equals 0?
The first df dy.
Df dy must be 0. So these would be the candidates. So we would have to solve that simultaneous series of equations. This does not prove that this point is a maximum or minimum. It just tells you if you are going to have an interior maximum or minimum, this is the only chance you have. You've got to have these partials equal 0. Now there was a comment about a second derivative test. In one variable, if I give you a function, f prime is its first derivative, f double prime is its second. We have two first derivatives now. How many second derivatives do we have? 4. What are the second derivatives? What 4 ones do we have?
fxx,
fxx,
fxy,
fxy,
fyx,
fyx, which may or may not be the same as fxy,
and fyy.
and fyy. Okay. Most of the semester, if I ever ask you what class would be really useful to know right now, the answer is yeah, there seems to be a split. It's mostly real analysis. But today is one of those special days where linear algebra would be useful. And so if you knew linear algebra, the following fxx, fyy minus fxy squared, it would actually make sense as to why the hell we're studying that. This is what leads to the analog of the second derivative test. We will get to that probably later in the semester. This is not a bad way to give you a brief introduction to linear algebra. Related to this is, how many of you remember the conic equations from high school, from Algebra 2? The ellipses, the hyperbolas, right? How many of you remember the equations of them? how do you remember the equations of them if they're not aligned with the x and y axis? They normally don't do that in high school. But if you know linear algebra, they're all the same, and there's a really nice compact way of writing them all down. And that actually explains why something like this becomes the maximum and the minima. So what I want to do is, again, if there's material that you want me to cover in class, let me know. Put comments on the Excel sheet, or I guess it's called a Google sheet, on the Google sheet. Email me and say, Professor Miller, make sure you cover this. If not, I'm going to use the extra class time and say, well, okay, I'm assuming you're all fine with the lecture, and I'll talk about stuff like this. I'll talk about the deeper theory and why things work so that you're not just computing, that you have some sense. This looks like some kind of strange magic, writing an expression like this down, that's what we want to study. Where does this come from? Why is this a natural thing to look at? Why is this the combination of second derivatives? The only thing I can say nice about it is at least both terms have the same degree. They're both two terms. And really, how do you think fxy squared should be written?
fxy times fyx.
Yeah, it should really be written like that. All right, so this is the beginning of multivariable optimization. And we will do one of my favorite applications of this. How many of you have taken a stats class? I took one from the psychology department as an undergraduate. I'm not quite sure if that counts. One of the big things you learn in statistics is the method of least squares or linear regression. And it turns out that the theory of linear regression all comes from this set of equations right here. And we will do that. And I will talk about real-world applications. I've actually just done a $3.5 million application for the school districts of Williamstown and Lanesboro, which led to the two towns agreeing to regionalize. And so I will give you some real-world data as to not just fake numbers. I'll also give you some astrophysical data where this was used to help find, or could be used to help find things such as Kepler's law. So you already have enough stuff to do incredible applications. All right. I want to do Farmer Barbara. So what shape do you think Barbara likes? I'm sorry? Not a circle. Triangle. That's why I played They Might Be Giants Particle Man, because one of the characters in Particle Man is Triangle Man. All right? Farmer Barbara. She loves triangles. If she has a given perimeter, she wants to find which triangle maximizes the area. What do you think the candidates might be? Doesn't have to be the right answer. I'm just like, what possible triangles do you think might work, might give you the best answer? Equal out triangle. Great candidate. Any other candidates? Right triangle. Any right triangle or specific right triangle? Yeah, maybe the isosceles right triangle. But it might just be, maybe it doesn't have to be isosceles. But just, since there are infinitely many right triangles, maybe the isosceles right triangle in some sense is the best. To me, these are the two most natural shapes to look at. And what we want to do is, given x plus y plus z equals the perimeter, we want to maximize the area. So here's x, here's y, here's z. Here's our general triangle. So we need a formula for the area of the triangle. Does anybody remember the formula for the area of a triangle? Base times height, but that we don't have, unfortunately, the height given naturally. I want the area in terms of x, y, and z. If I specify the three sides, does that uniquely determine the area?
Is this like are you talking about like the hero? Is that
Yes.
the hero one?
So it's either Hero or Heron's formula. I think you're allowed to put in the n if you want. So does anybody remember the formula? So let's let S be the semi-perimeter, x plus y plus z over 2, then the area is the square root of s minus x, s minus y, s minus z. Does anybody remember this formula? Or does at least something like this look familiar? How can we check and see if I've remembered it correctly? What do I know? What do I know related to triangles? Are there any triangles whose sides I know and I know the area?
Area of the right triangle.
Which one?
3, 4, 5.
3, 4, 5. So if I take the 3, 4, 5 triangle, the area is 6. The semi-perimeter 5 plus 3 is 8 plus 4 is 12 divided by 2 is 6. And I would get then the square root of 6. 6 minus 5 is 1. 6 minus 4 is 2. 6 minus 3 is 3. The square root of 6 times 6 is 6. Does this prove Heron's formula? No. But does this make you more comfortable? Yes. Right? And at least pass the test with a 3, 4, 5 triangle. Right? So it's a beautiful formula. All right. So our goal is to maximize this function, and this looks like a legitimate three-dimensional function. And even if I somehow replace z in terms of x and y, I'm still going to have a function of two variables. All right, this is a legitimate problem. Can anybody think of a function that's better to look at than the area to maximize? That would be equivalent to maximizing the area. What don't, yes?
The interval.
I'm sorry?
The interval.
Well, we don't, what would we be integrating? We don't really have an integral here.
You do area squared.
The area squared. Excellent. Why would we do area squared?
Get rid of the square root.
The area is the square root. If I maximize the square of the area, have I maximized the area? Yeah. There's a nice one-to-one relationship between them. So, and so this is going to be fixed. So is it enough to maximize this function? What do you think?
Where did the S go?
So I dropped the s. Am I allowed to drop the s?
That's not what the S is.
Well, I'm telling you, s is fixed. S is always fixed for this. I'm giving you a fixed perimeter. So if the perimeter is fixed, the semi-perimeter is fixed. Let's choose a specific value. What value would you like the semi-perimeter to have?
20.
Nope, try again.
30.
Nope, try again.
0.
I just heard it. 1. Right? Nice number 1. You can choose your units. Anybody know what the unit smoot is? So this is one of the reasons we do not have fraternities on campus. Fraternities are sometimes known to do cruel things to pledges. One of the fraternities at MIT decided they wanted to know how many smoots, if he was a pledge, it would take to go from one end of the bridge to another. And they just picked up smoot and kept marching him down. The smoot is an accepted unit of measurement now. We may actually cover smoot later in the semester. He had a very interesting life. Another unit the MIT students gave us is the Bruno. It's the indentation in cubic centimeters from dropping a grand piano from the third floor of a building onto concrete. You can create whatever units you want. There's other units that I don't want to say in public. There's a lot of units that have been created. You can ask me after class. They're interesting people. Okay? Choose units to make the problem nice. If I were to double P, I would just double X, Y, and Z. Would I change the shape of the triangle? No. The area would go up by a factor of 4. If I triple P, I just triple X, Y, and Z. I don't change the shape of the triangle. So I might as well choose units that are nice. If I want, I can choose the unit so it's 1. I could change it to be 20, I could change it to be 3, doesn't matter. But why not just make it 1? So in that case now, what's the perimeter? Perimeter would just be 2. So since S is always going to be fixed, if I maximize this, that's the same as maximizing this. Okay? And so now I really have the function f of x, y, z is just 1 minus x, 1 minus y, 1 minus z. What are the possible ranges for x, y, and z? So when you look at x, y, and z, yes?
Well, wouldn't they have to be greater than or equal to 0
Good.
and less than or equal to 1?
Yeah. You're not going to have a negative length. And if I have a triangle, one of the great facts about a triangle is the sum of any two sides is greater or equal to the third side. If I have a degenerate triangle that's just a straight line, then the sum of two sides equals the third. But as I start going up like this, the sum of the two lengths would be larger. There'd be an overlap as they come down. So if the perimeter is 2, what's the largest a side could be? Could I have a side of length greater than 1? No, if x plus y plus z has to equal 2, if x is greater than 1, say x is 1.5, then y plus z can be at most 0.5. So does everyone agree that 0 less than equal to x, y, z less than equal to 1? Yes?
Question about notation.
Yes.
Why do you write less than or equal to, or equal to?
Well, because they could be equal to 0. There'd be a degenerate triangle, but I'm allowing myself that possibility.
How does your perimeter 2?
Well, I'm saying I chose units so my semi-perimeter was 1. So if the semi-perimeter is 1, the perimeter is 2. Right? The semi-perimeter is the perimeter divided by 2. So that means x plus y plus z must equal 2. All right, so I have a function of 3 variables. I have my constraints. Do you think the optimal value is going to occur at one of the boundaries? No, what am I going to get at the boundaries?
0.
All right, great. So how do I find the maximum minima? Yeah, so how would I find the critical points? I would want what? All right, so I want df dx. And so when I take the derivative of this with respect to x, that means y and z are constants. So what's the derivative of 1 minus x with respect to x? It's just minus 1. So I get minus 1 minus y, 1 minus z. Okay. I take the derivative with respect to y, and I get negative 1 minus x, 1 minus z. And I take the derivative with respect to z, and I get negative 1 minus x, 1 minus y. And because I'm trying to find critical points, they should all be 0. All right, so now we have 3 equations, 3 unknowns. Let's solve. What must be true? So I want 1 minus y, 1 minus z to be 0. What does that tell us? I'm sorry? One of them equals 1. So without loss of generality, let's say y equals 1. If y equals 1, then we're okay over here. And then what do we learn from this one? One of them also equals 1. So x equals 1. So basically, at least 2 equal 1. Oh dear. What's the perimeter of the triangle? 2. If 2 of them equal 1, what is the third? 0. Huh. We've just shown that the maximum triangle has no area. Crap. I hope I'm doing a good job of looking confused right now. It's really hard to do the same lecture twice in a row and pretend twice. This is just, full disclosure and honesty. Okay, so obviously we did something wrong. Obviously I got something by you all. Where did I slip it by you?
When you left off the constant, maybe?
So that's one possibility, is maybe dropping the s mattered. But I'm doing this problem where s is fixed. It does seem like that's a candidate. I agree with you that that is a candidate. That maybe dropping s was bad. But I'm constraining myself so that the semi-perimeter is fixed. That means the perimeter is fixed. So the thing I dropped doesn't change. So
When you square it?
when I square, well, if I'm trying to maximize, a positive number, that's the same as maximizing its square, because there's a one-to-one correspondence. What numbers square to 4? 2 and negative 2. So 2 numbers square to 4. But if I restrict myself to positive numbers, only one positive number squares to 2. So studying a square and studying a square root, it's the same for maximizing. You often get problems, which point is closest to a curve? Rather than looking at distance, you should look at distance squared. So the mistake is really subtle. I'm looking at 0 less than or equal to x, y, z less than or equal to 1. What kind of object is that? 0 less than or equal to x, y, z less than or equal to 1. So x is between 0 and 1, y is between 0 and 1, z is between 0 and 1. What kind of shape is that? Not a sphere. A sphere would be x squared plus y squared plus z squared is less than or equal to 1. It's a cube. This is almost the level of my artistic talent. We have a cube. Let's think, is the cube the right region? What do we know about x plus y plus z? X plus y plus z is supposed to equal what? 2. That's the right constraint. Now, for the constraint x plus y plus z equals 2, it is necessary that each of x, y, and z be between 0 and 1. But it's not sufficient to just look at those points. Not all of those points are valid candidates. So what kind of shape is x plus y plus z equals 2? I think I heard it from this part of the... It's a plane. So x, y, z, that's 3 variables. I have one relation between them. This is the equation of a plane. It's a plane with the normal vector 1, 1, 1. 1, 1, 1 dotted with x, y, z equals 2. This is the equation of a plane. I am not looking at this entire box. I'm actually looking at a plane slicing through that box. So a lot of the setup we did here was correct. But I deliberately wanted to do this to show you how easy it is to make mistakes. When you do integration by parts, this is one of the techniques you must remember for this course. I will probably avoid, like the plague, partial fractions and trigonometric substitutions. I know you love doing those, I apologize. But you have to do integration by parts. I love to write u equals, dv equals, du equals, v equals. It takes a little bit more time, but then it's clear what is everything when I'm using. You really want to spend the time and think carefully about what's going on. When I wrote this, I was too cavalier. I was too careless. And I said, this is the same as this problem. No. So for extra credit, do the analysis correctly. Try to figure out what triangle has the greatest area. What do you think it's going? Yes.
Well, I just had a question. So, like, what exactly was how do you fix the mistake?
So the mistake is I was trying to use interior points and say I have a cube, and I know that the maximum can't be on the boundary of the cube. So I now can look in the interior. And the interior includes points I should not be looking at. It includes points where x plus y plus z is not equal to 2. I can only look at points where x plus y plus z equals 2. So for instance, if I take them all equal to 0, I would get a value of 1, which is the largest value. If I take them all equal to 1, I would get 0, which is the smallest value. And so I'm looking at too many candidates. I want to look at just the candidates where x plus y plus z equals 2. So instead of looking at Brown and Bob and Barbara and just trying to find more B names, the general question is, if I give you some curve, what shape do you think encloses the largest area? Circle. And if I give you a fixed surface area, what shape do you think encloses the largest volume? Sphere. And so in fact, most of the time, buildings are not made cylindrical, even though that would be better area-wise because of human issues in terms of what we want to live in. All right, this is a good place to stop.